Section 13.5 is curl and divergence. These are two differential operators or partial differential operators that we're going to introduce. It's kind of a nice section. It's mostly just calculation with these two differential operators. So it's kind of almost fun in some sense. So we start with the curl, and we'll look at a vector field F, which has components P, Q, and R, all three of which are functions of X, Y, and Z in R3. And we'll assume that the partial derivatives of P, Q, and R all exist, at least for this instance. The curl of F, of this vector field F, is the vector we see on the right-hand side, partial R with respect to Y minus partial Q with respect to Z. It's the first component. Then we have a second component, P with respect to Z, R with respect to X. And third component, Q with respect to X minus P with respect to Y. So that is our curl. And to simplify our notation for the curl of F, we'll use this gradient operator here, or del. Del is equal to this vector operator, or we can define it to be equal to this vector operator, where really we have it written here in standard basis components, but we can see it also as a vector that would look something like this. Partial with respect to X, partial with respect to Y, partial with respect to Z. And for even more concise notation, partial with respect to X, Y, and Z, using the capital D notation, really kind of cleans things up and keeps it simple to write all this down. So what this means is that if we take this operator del and cross it with the vector F, we should be able to come up with the curl. Or if we first apply it to a scalar function, just to see it in this regard, the application of del to F is the gradient of F. Okay, so, well, that's what we've done in the past with this, but we see that for a scalar function, the gradient of it came out to a 3D vector. Scalar function of three variables, X, Y, and Z, has a gradient vector, which a three-dimensional gradient vector. Now let's apply that to the curl scenario, right? So if we treat del as a vector, then we can cross a 3D vector with a 3D vector, F being the second vector here, and we end up with the curl of F. The reader can verify that this is the case by noting that del cross F, cross product F, is I, J, K, and then partial X, partial with respect to Y, partial Z, and then P, Q, R, and carry out that cross product, and we'll find that we get exactly what's in the box up here. Okay, so those things should match, and we'll see that that's a nice notation for writing the curl of a vector field down. So let's have a look at an example. It's a pretty straightforward calculation. It's essentially just going to be this determinant, 3x3 matrix determinant each time. So we have I, J, K, so we're given a vector field F in terms of X, Y, and Z. And we're asked to find the curl of this vector field, and we recall that the curl is equal to del cross F, and that's this matrix determinant. The way I've written it now is by cofactor expansion. So I'm expanding along I, J, and K. So for the I position, cross out the top and the top row, first column, and we find this 2x2 determinant. Wherever a differential operator is multiplied by algebraic term or a function, then we apply that derivative, that partial derivative. So this first one is the partial of this with respect to y, which gives us xz squared, and then minus partial z of xy squared z, and that gives us xy squared. Now, or we can just do the old diagonal method that we've used in the past for these, whatever you prefer. Cofactor expansion is a nice way to do these if the student's comfortable with that. So then minus the j position, so we cross these out and we do the determinants of partial with respect to x of this minus partial with respect to z of this, and that gives us these two terms. Similar for k, top row slashed out, last column slashed out, and we do this determinant, and that gives us that difference. So when we're done, we find that the curl of this vector field is this. Another way to do this would be just to use the formula on the previous page. I think it's probably harder to remember that formula than it is to do the vector or the matrix determinant, but either way, the student can decide. So yeah, let's look at our first theorem involving the curl. So if f is a function of three variables that has continuous second order partials, then the curl of the gradient of f is equal to the zero vector. Now let's be sure of some things here. F is a function of three variables, so it's a scalar function. When we take its gradient, that becomes a 3D vector, since it's a function of three variables. And now we're taking the curl. Remember, the curl is del cross gradient of f, and they're telling us we get a zero vector out of this. This is a 3x3 vector crossed with a 3x3 vector, and the result of a cross product should be a vector of the dimension of the two products in the cross product, so the two multiples in the cross product. And that's exactly the case. So just to make sure that our notation makes sense in terms of vectors will go a long way to tell us whether or not we've got a viable expression or a meaningful expression in this notation. So let's prove this theorem. So we assume that f is such a function. It's a function of three variables with continuous second partial derivatives. And we have a look here. We start out with the curl of gradient of f. And well, the gradient of f is partial f with respect to x, f with respect to y, f with respect to z, in each of the first through third components. And then the curl cross with that vector is the matrix determinant we have right here. And doing these in cofactor expansion or by diagonals, however we choose to do so, we come up with this vector here. And we see that thanks to Clairaut's theorem, each of these second partials can be swapped in terms of order, so they're actually equal to each other. So each of these terms and each of these components is zero. So we do in fact have the zero vector. That's the result of taking the divergence, the curl of the gradient of f. Okay, so it's a nice fact to have around. We can use it to check whether or not a vector field is conservative. And recall that if f is a conservative vector, this is a corollary to the previous result. Excuse that. So if f is a conservative vector field, then the curl of f is equal to zero. Okay, so the reason that should be the case is that if f is a conservative vector field, then there exists a scalar function f such that the gradient of f is equal to the vector field f, and we just saw that the curl of a gradient is equal to zero, so the curl of that vector field f would have to be zero. So this is yet another way to check to see whether or not we've got a conservative vector field, or to recognize one if should the opportunity arise. So the converse of this fact is given by the theorem below. If f is a vector field defined on all of R3 whose component functions have continuous partial derivatives, and the curl of f is equal to zero, then f is a conservative vector field. So we have a full characterization. In other words, the implication works both ways. If the curl of f is zero, f is conservative. If f is conservative, then its curl is zero. So let's use this fact down below in the two examples we have. Determine whether or not each vector field is conservative. If it is, find a scalar function f such that gradient of f is equal to the vector field f. Okay, so our first vector field is the function we did in the previous example, which had curl equal to this function, which is not identically zero. There are values of x, y, and z for which this is not equal to zero. So f is not conservative in this case. Okay, now next we've got part B. We have a new function. We haven't found the curl of this vector field, so we'll do the work here. Again, it's this matrix determinant, and this has been broken up in cofactor expansion. So this subdeterminant is here, times I, minus the subdeterminant canceling out j in the first row, that's here to here, and then plus this subdeterminant times k. Okay, doing cofactor expansion, applying the partial derivatives wherever a d sub x or d sub y or d sub z operator hits a function. And we find that when we total all this together, that we actually do get the zero vector out. This is zero, this adds to zero, and that adds to zero. So we have a zero vector, which means that from above, f is a conservative vector field from the above theorem. Since f is conservative, we can now look for a scalar function f such that the gradient of this function f is equal to the vector field. So in other words, an f that satisfies this property right here is what we're trying to find. In order to do that, we're going to integrate each of the components of f. First component with respect to x, second component with respect to y. So we see that happening here. First component with respect to x, and we have a second component with respect to y, and a third component with respect to z. Somewhere on the list as well, that is down here. Only the integral is not written because we see what we need to do. So we find antiderivatives with respect to x, and that gives us this expression. And we do the same for y. Remember that we're going to add g sub y of x, or g of yx, or sorry, g of yz, because there could be some function of y and z that was not included in here, or that didn't include an x in its argument, or in the definition of its function, that could show up or have been zeroed out by the partial differential operation that got us this first component of capital F. So instead of a constant of integration in all of these, we have this function of integration that was constant with respect to the variable of integration. So in the second one, we integrated with respect to dy. So there could be a function of x and z that was zeroed out when we took the derivative in the first place to get the vector field f that we were given to start with. Okay, so we do that for all three cases, but then we look to see what matches, right? This term matches this term, matches this term, and there's nothing more in any of these function definitions other than these would-be possible functions g, h, and k. But since there are no extra terms to account for, g, h, and k can all be chosen to be 0. And that's exactly what we do, and we know that our scalar function is this. Now it's easy to check, in this case, that the identity gradient of f is equal to the vector field f by just applying the gradient of f and going to work. Okay, so determining a vector field f, a scalar, whether or not a vector field is conservative, and then finding the scalar function which is equal to that vector field in gradient. Okay, so we'll move on, and we have divergence now. So the divergence is another operator that uses a sort of a vector calculation with this del operator. First, though, we define the divergence of f being, again, a vector field in R3 with functions p, q, and r that all have partial derivatives. And the divergence of f is p with respect to x, q with respect to y, r with respect to z, all partials and added up. So note that the result of the divergence of a vector field is a scalar. This is not a vector anymore. The partial derivatives are all added together as a scalar unit or scalar entity. So in terms of the gradient operator, we can write divergence of f as del dot f. And we see that that would be exactly the case up above. Del dot f this would look like, maybe I'll write it as dx, dy, dz, partial differentials. This is a vector. If we dot it with p, q, and r, or f, it's exactly what we get out of this. In fact, I'll put this here. Show that a little bit better on the right-hand side. So that is our del operator as a dot product, and it's going to yield us a scalar as we would expect from a dot product, and also that matches the fact that the divergence is a scalar. Okay, so compute the divergence of the given vector field. This is a little bit easier than the curl. We don't have so much work to do. The divergence of f, del dot f, is equal to partial x of the first term, partial y of the second term, partial z of the third term, and we work from there. Partials are all the same, more or less, it turns out, and we add those up to get 6xyz. The fact that they're the same is really just a coincidence. So that is the divergence, a little bit more simple than the curl. So let's move on. Turns out the divergence of the curl of a function f is equal to 0. And we'll present a proof of that in just a moment. So again, f is this vector function p, q, and r. The second partial derivatives of p, q, and r are continuous. We'll assume that to be the case. If it is, then the divergence of the curl of f is equal to 0. So let's prove that. And we'll note that the divergence of the curl of f is actually equal to del dot, in parentheses, del cross f. So let's check our vector quantities and make sure that these things, this is a meaningful expression. Del cross f, the curl, yields a vector, a 3D vector. And then this is a 3D vector crossed with this 3D vector, so we should get a scalar, and yeah, we see a scalar 0 on the right. So our dimensions all make sense, and our statement's meaningful. Now let's have a look at the proof. So we let f be equal to the vector field p, q, with component functions p, q, and r, and all three are functions of x, y, and z. And the divergence of the curl of f is now del dotted with del cross f. I dropped the parentheses because we're just going to operate in the way that makes plausible sense. We could not take del dot del first. That would be a meaningful expression in this case. So, unless we were to define such a thing. And the problem with that is del dot del, the dot product of two entities, should be a scalar. We can't take a scalar crossed with a vector. There's no definition for that. So in fact, that wouldn't work at all. Anyway, del cross f is just the curl of f. We can go to the very first page of the notes and write down the definition of the curl of f. This is what it would look like in its vector notation, not standard basis form with I, j, and k, but we just convert it quickly. Now we have del dotted with that vector, and that looks like this. Del d sub x of the first component, partial y with respect to the second, and z with respect to the third. And what we find now is we have mixed second partials, but since these second partials are continuous, Clairaut's theorem tells us that we can reorder them, and we'll see that r sub yx and negative r sub xy are equal to each other. Well, r sub yx is equal to r sub xy, so these two would add to 0 thanks to the difference in sign in front, similar with the q's and similar with the r's, with the p's. So everything adds to 0. It's a scalar 0 on the right, and we've established the theorem as intended. Okay, so the next question is there a vector field G on R3 such that the curl of G is equal to this vector function, or this vector field that we're given here? Okay, so is there sort of a parent field G whose curl is equal to this highlighted vector field we're given here, this vector function, we could even say? Now, to check for that, we're going to use the result above. If G, or if the if what we were given was the curl of some field G, then the divergence of this field of the curl of G should be 0. So that's exactly what we're doing here. We're going to find the divergence of what would have been the curl of G. Now this has to be 0 if there was such a field, vector field G, whose curl was equal to this. And let's check then. So that's thanks to this theorem here. Now, the divergence of this is, well, with respect to, partial with respect to x gives us sine y, partial with respect to y gives us negative sine y, partial with respect to z gives us 1 minus 0. So this adds up on the right to 1, which is non-zero. So this is not satisfied. This is a necessary condition if this vector field was equal to the curl of some vector field G, then the gradient or the divergence of the curl of G should be 0. Well, it couldn't be the case that this is equal to some curl of G vector field because our divergence was not 0. Okay, so that essentially handles that one. Now, had that been 0, then we could say, yes, it's possible that G was some vector, there is some vector field G whose curl was equal to what we were given here, because when we take the divergence of it, we got 0, and this necessary condition was still met. Okay, so using these facts in a slightly deeper way. Let's prove a result. There's a whole set of problems in this section where we prove identities for this del operator. Okay, this one involves the divergence, and so we assume that F is a scalar field, capital F is a vector field. There's no G in this problem, but there could be in other ones, and that all functions have appropriate continuous second partials or continuous partial derivatives, whatever it is we might need. In this case, we just need continuous partials. So we assume that F and little f are as stated above, and we'll say further that F is equal to P, Q, and R, component functions of x, y, and z each, and they have continuous partials as suggested above. Now, starting with the left-hand side, the gradient dotted with scalar function f times vector field f gives us this expression. And we know that, del dotted with that. Now this is our dot product occurring. First component of del times first component of the second vector. Second component of del applied to the second component of our vector, and the third component times the third component. Remember, multiplications for this dot product are actually applications of these partial derivative operators. So using a product rule for this partial derivative, we get the following, and then very similar for these other two. Okay, now regrouping terms, take all the non-differentiated multiples of the scalar function f, and we write that as such, factoring the scalar function f out. And we do similar thing, we collect the terms of the non-differentiated p, q, and r, which are each times f sub x, f sub y, and f sub z. And we see that over here, this is the gradient of f. So f times the gradient of f. And then on the right, we have, this is f dotted with the gradient of little f. And that's exactly how we write it off to the side here. So we started with the left-hand side, arrived at the right-hand side, and we've proved our identity as desired. So there are several of these. Be sure to expand these vector fields f, and if there's a g, you'll have to make up some letters for those parts. But that's one thing to remember, that vector fields have component functions of x, y, and z. Don't try to use something like, you know, if we started this and said, okay, there's f, it's not this. It doesn't look like this, that doesn't make any sense, right? You want to give each of these three functions and its components a new name. So maybe maybe in this case we do S in M, possibly something like that to match with P, Q, R, whatever it is the reader might prefer for letters there. Now, vector forms of Green's theorem. So the biggest question at this point is we're dealing with these new operations, but what are they really? What's the intuition? Why would we bother to have such operations around? What does this mean for anything we might study? This is a nice way to see what this might mean. So let's do a little bit of work to put together this first result in the box down here. And we'll suppose that we have a plane region D that has a boundary curve C. It's a simple closed curve C. We'll assume it's smooth, piecewise smooth at least, simple closed, all the nice things we need for Green's theorem. We consider a vector field F, which is equal to P and Q. And P and Q are each functions of X, Y. So there's no Z involved in this. So we're just considering a planar vector field or a vector field in R2. Okay, the line integral of such a vector field is given by the following. Seen this before, we can split this up into function P and Q and along X and along Y. Now let's take the curl of F after we embed F, the vector field in R3, by just simply appending a 0 to its third component. So we started, F was just P and Q, and we just say, okay, we can embed this two-dimensional vector field in R3 by just saying that its third component is 0. There's nothing happening in that third component. So now this sort of, with that 0 tacked onto the end right here, that makes this vector field a resident of R3, even though all the action that takes place in it is planar. It's in the XY plane. Okay, this will help us add some context to what's going on with this curl and this divergence operation. So if we now take the curl of F, note that that's del cross F, and we have this matrix determinant off to the right here that we could calculate. We can see where some of the zeros might come about immediately. It's because our third component in our vector field is 0. So, you know, partial with respect to y at 0 is 0, and then partial with respect to x at 0 is 0. Now, why do we get the other zeros that would come about? Well, note that P and Q are only functions of x and y. So anytime the partial differential operator dz hits P or Q, it's going to be 0. Okay, when we're done taking care of that and noting where things should be 0, we get this expression here. We get partial Q with respect to x minus partial P with respect to y in the K component. Okay, this is not surprising. We've taken cross products of two-dimensional vectors in the past and found that the result was a vector in the third dimension, even though the two vectors themselves only shared a two-dimensional space. Okay, so one way to think about this is to have a look at maybe a vector field, and in this case I'm going to speak about vector fields as flows for the rest of this page, or the rest of this section. So if this is some sort of planar flow, so maybe a very thin sheet of water moving along a surface somewhere, then what the curl seems to describe, and we'll see this a little bit further below, is, you know, suppose we have an eddy in our flow, right? So tracking a molecule or a particle of water that moves along this path right here, we sort of have this eddy situation. Well, the vector that is being rotated about is not actually in the plane. It's a point right here that things are being rotated about, but it's really sticking up out of the page, out of the plane that this water is moving in. And that's essentially what the curl is describing. It's the point, or the position of it here is the point at which the fluid flow tends to rotate about, and then the length of it would be the tendency of rotation, sort of the measurement of rotation. If it was 0, well, then there's no rotation about that point. If it's a larger and larger value of magnitude, then there's more or less rotation in a positive or negative direction. Okay, so that's an idea of what the curl is, and we'll see that a little further too in this next result. So, and the result in the beige box. So take this curl of f that we have, and let's dot it with k, the standard basis vector k, and we get exactly the term in Green's theorem that's in our double integral. Okay, so we swap that out in the double integral of Green's theorem, and we've got this vector form of Green's theorem. So where the two highlighted green objects are equal to each other, so we can rewrite Green's theorem in this vector notation. Okay, so what does that mean? Recall that Green's theorem, or let's note that Green's theorem around this curve C right here, a simple closed curve containing a region D. So dr is r prime of t dt. And so r prime of t is really the tangent vector along this curve C at any point along it. So this is the tangential form of Green's theorem. Using it's because we're using this expression on the left. Okay, there's a way to write it in a normal form, and we'll see that below. But this is the tangential form. If we look at this, what Green's theorem is telling us, and it's explaining something to us about the curl, we're looking at the line integral along this curve, right? So we're rotating in the positive orientation of C about the region D, and it's telling us that that's equal to the double integral of the curl of f dotted with k along this region. So what we see here is that we're connecting the curl to rotation about a region, or rotation along a curve. Okay, and that's what I was asserting up here, only now we've got it a little bit more directly looking at a simple closed curve C. So that's how we can relate the curl of f to rotation about a point, or rotation about along a closed curve in our vector field, by the tendency of the flow or fluid to rotate about a point or curve. Now we can rewrite this, and the book's got the details for this final result here. This is the normal component version of Green's theorem. If we work out all the details for this, we'll find that f dot the normal vector, remember the normal vector at any point t is, we can calculate such a thing. There's a nice handy way to do it in the book because thanks to an identity that they provide. But if we have the same curve C, but now we consider all of its normal vectors, the vectors pointing outward or possibly inward into the region D along its boundary C, or out of it along its boundary C, then that's actually connected to, through Green's theorem, the divergence of f. So we can get some idea of what the divergence of f actually tells us. It's a measurement, or it's an implication as to a tendency of flow to leave this region D, or say these normal vectors were pointing inward, negative direction, flow inward, or a tendency to flow into this region. So the curl tells us about rotation. The divergence tells us about a tendency of the flow to leave, or sort of, I guess, use the word converge, to move into a region. So, and we can see that that's got some implications in the study of fluids, or any sort of field, a magnetic field or electric field, gravitational field. So we can see what utility there might be in divergence and curl. Otherwise, it's just a nice set of calculations, and the student probably shouldn't have a very hard time carrying out all the calculations of this section.